Here I have two molecules, R and S thalidomide. One is used to treat morning sickness, while the other is a toxic chemical. Other than the fact that these two molecules mirror one another, they're exactly the same. So what causes such a drastic difference between their effects? To uncover this mystery, we must first understand chirality. Atoms in our world undergo chemical reactions, allowing for the creation of new molecules, each different from the rest. But even with 118 elements, there exist molecules with the exact same chemical formulas. Does this mean they're identical? Not necessarily. This is where isomers come into play. Isomers are molecules with the same chemical formula, but their atoms are arranged differently, resulting in two different structures. For example, lavender and orange oil both contain the molecule linalool, but have distinct smells. Even with the same formula, the structure of each linalool varies, changing its properties. Now there exist two types of isomers, constitutional and stereoisomers. Constitutional isomers have structural differences, with their compounds' atoms making different bonds. On the other hand, stereoisomers have the same bonding patterns and instead differ in their atoms' spatial arrangements. So what exactly do I mean by differing spatial arrangements? Well, this can be partially explained with chirality. Chirality defines two molecules that are mirror images of one another. To understand this, let's look at a pair of earbuds. Both the left and right earbuds are made of the same materials with matching structures. Their only difference is how they mirror each other, making it impossible for them to superimpose. The same applies to chiral compounds. These molecules remain different because of their mirroring, but chirality only occurs if certain conditions are met. First, almost all chiral molecules have a central carbon, which can create up to 4 bonds. Secondly, all 4 bonds surrounding the carbon center must be different. Let's see why. Whether we have 3, 2, or 1 identical bonds in a central carbon compound, they can always be rotated and translated to match their mirrored image. But once each bond is unique, rotation or translation fails, forming 2 unidentical mirrored molecules. So why does any of this matter? Well, the human body works using shape-sensitive cell receptors. These cell receptors are like puzzle pieces, with both the receptors and their ligands fitting perfectly into one another. If you use the wrong pieces, they simply won't match. Now remember our earlier thalidomide example? The R thalidomide will attach itself to specific cell receptors, stopping morning sickness, while S thalidomide attaches to the DNA inhibiting certain genes. Mistakes in detecting these chiral molecules when making medicine can lead to toxic drugs or ineffective ones. So with the power of chirality, never underestimate the little things, because they have the power to make a big impact.